Okay, so good morning, guys. Let's start. Yesterday we introduced the transport layer, just reviewing the main functions of this layer. Now we are getting into the details of the protocols that used in this layer. We start with the UDP, which is a connectionless protocol, so is not used by applications that requires the setup of a connection before sending data. And instead it is useful for sending short messages. The name is, the acronym UDP stands for User Datagram Protocol, and the name recalls that the fact that the segment, that is the protocol data unit at the application layer, in case of UDP, is practically coincident with the segment, with the packet at the IP layer. Okay, so that is the datagram. And this is why it is called User Datagram Protocol. In particular, each segment of UDP is encapsulated in one and only one packet. Okay, so the relationship between packets and UDP segments is one-to-one, while for TCP is not like that, okay, as we will see. So since this protocol does not guarantee any quality of service, also the header that is added at the transport layer is very thin. You just need very few information to manage UDP. And practically the header reflects the only two functions that are performed by UDP. One is application addressing with multiplexing and demultiplexing, which remains, and the other is error checking, which is a simple check of errors, but there is no mechanism to perform error correction. Okay. So it is only checking. Moreover, it is also optional, and this the performance, the error check is optional. It can be disabled. So in the header is the green rectangle you see in the picture. It has two words of 32 bits. This format of listing fields of the headers in rows of 32 bits is very common, and you will see it both in the transport layer and also in the IP layer. And basically it is like that because it reflects the logical structure of the IP packets. And the main field of the IP packets, in the header of the IP packets, as you already know now, is the IP address. Okay, the IP address is 32-bit long in IP version 4. So all these headers are represented graphically as rows of 32 bits. 32 bits means 4 bytes or 2 groups of 16 bits. So in this case, the header contains only 2 rows of 32 bits. The first one is split into parts: source port, destination port. Okay, as we've seen yesterday, the port number is 16-bit long, so you have the space for the source and destination port. Second field, second row on the first field on the left is the length of the segment, including the header, so this is 8 bytes, plus the payload. Okay, this is the number that is written there of 16 bits. So field 16 field is used to represent the length measured in bytes. Okay, so the number of bytes that are composing the segment. Finally, there is the checksum. The checksum contains the redundant information generated when the segment is transmitted, so that when the segment is received, the error check function can be carried out by the receiver. Okay. Why we should use UDP instead of TCP, since the UDP is so poor in terms of performance? We have already covered this issue. It is used in applications that need fast transmission of information and accept or tolerating errors. Okay, so when the trade-off is between correctness and the transfer speed is towards transfer speed, you can use UDP, and so it is very used for all real-time applications like video conferencing, video streaming, and so on. It is clearly very simple, so you don't need to take to track the status of the connections in the receiver and in the sender, and it's based on very few rules. That is exactly the opposite for TCP, as we will see later on. And of course, the header is also shorter than a TCP header. The checksum is optional, and it is carried out in a very particular way. So here you see the UDP segment that starts with the green fields, and then you have the header and the data. The fields that are represented on the top in brown, they don't belong to the UDP segment. Okay, they are called pseudo headers, since basically are read and then used by the sender and read from the IP packet that will carry the UDP segment, UDP datagram. Okay. And in particular, you have the source IP address, destination IP address, the number of protocol, that is another field we will see when we will talk about IP packets. This number says that the content is UDP, basically. So it's a number that is associated to UDP protocol. So source IP address, destination IP address, and the protocol number are copied by the operating system from the IP packet that will host this UDP segment. And then there is the UDP length, that is the replica, exact replica of the length field. Okay. You don't find it in the IP packet, it's just replicated by the operating system. So once the original UDP segment and all these additional fields that makes the pseudo header are put together, then the transmitter starts the encoding process. During the encoding process, the checksum field is zeroed. So it's in the checksum field you find a sequence of zeros. At the end of the encoding process, the transmitter or the sender calculates the checksum. So the calculated value of the checksum is replaced, copied inside the checksum field before the segment is transmitted. Okay. Then the segment arrives to the destination with the checksum field that contains a value. So the destination can carry out the error check operation and understand if the packet has been transmitted correctly, if the UDP datagram has been transmitted and received correctly or not. So if there is an error, UDP will notify the layers above, will not take any countermeasurement against the error, but will notify the layer above. This is how it works in very generic terms. What is this say method to calculate? What is the method to calculate the checksum and to detect errors in possible errors in reception? So the answer to this question is contained in the next slides that are only inserted just for completeness, but you don't need to go into the details because this operation is a little bit complicated. So actually I didn't have time to translate them, but you can understand them quite well. So if you want, you can have a look. Okay. Remember that this method of checksum calculations and error check is optional in UDP, but it is compulsory in TCP, and the TCP applies exactly the same, using the pseudo header and the operation. Just go through quickly. There is a very strange arithmetic that is used to make these calculations. Basically, the calculation is based on the sum. So you take all the fields that we have seen here, so pseudo header, all the fields of pseudo header, all the fields of the UDP header, and the data. And the operating system split all these fields in blocks of 16 bits. So you have 16 bits, sequence of numbers of 16 bits, binary numbers, and then they are summed one to the other. So when you use this very specific arithmetic that is called complement one arithmetic, the numbers are summed bit by bit, and each time you have you sum two ones, there is a carry that is summed to the so first you start summing from the least significant bit that is on the right, and then if there is a carry, the carry is summed to the next bit going to the left. Okay. So for example, in this case, we have 0 plus 1, that is 1, and that's the result. 1 plus 0 is 1, 1 plus 1 is 0, and then there is a carry that is summed in the next bit. So it's 0 plus 0 plus 1 that comes from the previous bits, and so the result is 1, and so on. When you arrive to the last bit, the most significant one, if there is a carry, this is summed to the first bit. And that's called wraparound. And then this sum is repeated, summing all the blocks of 16 bits until there is a result that is the sum. And then the result before being copied into the checksum field is complemented. So it's negated. Each bit is so the logical negation of each bit is used. Okay. So this is the scheme that is done on the transmitter side. The checksum is initially put to 0, and then the result is copied into the checksum. This is an example. You can have a look. You have UDP segment, and by the way, this is the segment that is generated by an application layer protocol that is called Telnet. We are seeing it during the quick, fast lab session with the virtual machine. The Telnet is used to implement a remote terminal, and so basically messages of Telnet contains ASCII encoding or text. Okay? And it uses UDP as a transport protocol. So each message is encapsulated in a UDP segment that then is sent by in an IP packet. This is a segment. Here you have the representation in terms of binary numbers. If you have some bits that are missing, so you don't have an integer multiple of 32 rows, then padding is used, so zeros are added at the end. And then this is the sum, and the checksum is the value that will be written in the checksum field. On the receiver side, the receiver makes exactly the same operation as the sender, and given the properties of the arithmetic that is used, if the result is a sequence of zeros, so a sequence of ones, and then complemented with a sequence of zeros, then the packet is correct. Otherwise, if you don't have, if you have different numbers, the packet contains at least one error, so it's discarded. Okay, and this is what happens in the receiver, on the receiver side, on the same example that we have seen. Here you see that now there is the checksum value that has been calculated by the sender, and in this case, the segment has been received correctly, so you don't have any error, and you see that the sum is all ones, so that the complement is all zeros. If we introduce an error, for example, here, so I changed one of the bits from 0 to 1. That means that an error the transmission error has taken place. You see that the sum is not, the final result is not all zeros. So this segment has to be discarded. Okay. So this is a very common procedure that is actually very similar to all the kind of error checks that are made at different layers. Usually error checks works in this way. Okay, so you can have a look then later more closely.
Excuse me.
Yes.
There's a problem with the slides you put online, because they go from slide 14 directly to slide 21.
Yes, because the first version
Okay.
I put on a first version where I didn't print these slides and they were hidden.
Okay.
But I'm going to put a new version with all the slides. I also made a lot of changes this morning, so we will have a look to Wireshark maybe next week, just to have a look at the UDP packets. So now let's go on, and before going to the details of the TCP protocol, we have to introduce a generic concept that is the reliable transport. How can we make an unreliable connection reliable to an upper layer? And by unreliable connection, we mean that during transmission there may be some transmission error, and the reliable transport, the reliable service is given or provided to the upper layers if this layer that is carrying out the function is able to correct all the errors, or at least most of the errors. So the concept that we are introducing is general because it can be applied. The techniques that we are going to explain can be applied at different layers. To make a connection ideal, all the packets have to arrive with the same order, so in order, and moreover, we have to guarantee that all the packets are correct. Okay. If there are errors during the transmission, the function of the layer has to detect these errors and apply some techniques in order to correct the errors, maintaining the sequence of the packets at the receiver. What is the technique that allows to recover errors? Actually, there are two possibilities. One is called forward error correction, and in case of FEC, forward error correction, data are encoded by the transmitter with smart coding techniques so that the receiver not only can detect the error, but can also understand where is the error. So what is the bit or the bits that are changed compared to the transmission, to the original version. And once you detect the bits, then you are also able to correct all the errors. FEC is a very powerful technique that is adopted in most of the cases at the physical layer. Okay, so, for example, in radio transmission or optical transmission is very much used. We will not go into that case because actually it's basically only a matter of applying encoding techniques. So it's more a matter of for block encoding or convolutional encoding and so on and so forth. We will have a look to the other technique, that is retransmission. Retransmission means that each frame that is received correctly by the receiver is positively confirmed with an acknowledgement or ARQ message that is sent back to the sender, to the transmitter. This, of course, implies that the receiver has the capability of error detection, and we have just seen a method for doing error detection. In some cases, we can not only acknowledge frames that are received correctly or packets that are received correctly, but we can also negatively acknowledge frames that are received that have errors, that have not been received. In this case, the message that is sent back is called NAC, negative acknowledgement, or not ARQ. And we will see that you can apply this second method only in specific cases. When the transmitter receives a NAC, or in a given time it receives nothing, so it doesn't receive any ARQ, this indicates the need of retransmitting the packet. Okay, so the transmitter proceeds to retransmit the packet, and this procedure is repeated until the frame of the packet is correctly delivered to the destination. So at the end, the transmitter receives finally, at the end of the day, an ARQ. This system requires a return channel and service messages. The service messages are the ARQ and ARQ, and the return channel is needed because on one side the transmitter sends data to the receiver, on the other side the receiver has to send back the ARQ and the ARQ. And we have also to notice that these service messages are messages, so are packets as well, and so they may be corrupted by errors during their travel back. Okay? While they are traveling back, errors can also occur on ARQ and ARQs. So the system must be robust also in case of missing ARQ or missing ARQ. This type of procedure that is called the ARQ protocol, so the retransmission, can be adopted at different layers. Historically, it was also present at data link. So many protocols at data link layer in the past, especially in the past, adopted these techniques. Okay, so the data link layer was able to provide to the network layer a reliable connection between one point and another. Data link layer, as the name says, is a protocol layer dedicated to the management of point-to-point connections. So dedicated to the management of a single link. So each instance of the data link protocol is responsible of a single link. So this means that when you are applying retransmission systems at the data link layer, they are applied link by link. Each link is a retransmission, has to set up a retransmission mechanism. This, of course, increases the complexity, and so sometimes it's not so desirable to have this mechanism implemented at data link layers. In modern systems usually do not implement this mechanism of recovery at data link layers. For example, Ethernet for fixed lines does not have any retransmission technique inside the Internet protocol, and this because so we can simplify the procedure, and also because the physical transmitters, the physical transmission links have become more and more reliable compared to the past. And also, if you want, because FEC, forward error correction, is applied at the physical layer. This mechanism today is very much adopted at the transport layer, and in this case it will act end-to-end, because you know that the transport protocol is implemented only into host. And in particular in IP, so TCP/IP, this recovery mechanism is never adopted at the network layer, because IP does not have any mechanism of this way, and so it must be implemented in the transport layer. And TCP is exactly the implementation of this error recovery mechanism. So we will see then more in details how error recovery is carried out at the transport layer in TCP. So the protocols that manage retransmission are called ARQ, that means automatic request, automatic repeat request. The objective is to maintain packet integrity, order of sequence, avoid data duplications, and according to the specific type of protocols, only ARQ can be, in some cases, only ARQs are used, or sometimes also NUCs. There are not only these service messages are needed, but also other two mechanisms that are the timeout and the transmission windows. So now we will have a look at timeouts and transmission windows. This is an automatic repeat request. So the first, there is a family of ARQ protocols. The best known are basically three. One is called stop and wait. The second is called go back N. The third is called selective repeat. We will look only to stop and wait and go back N. Selective repeat may be some exercise, but it's more complicated. So the first one, the simplest one, is called the stop and wait, and it's a protocol that uses only ARQs, does not use negative acknowledgement, and it also uses a timeout counter. It does not use windows. The principle is very simple. Each message received correctly is confirmed by the receiver. That's all. Okay? So each time the receiver receives a message that can be a packet or a frame or a segment, then it sends back an ARQ to the transmitter. So how the transmitter can understand if the packet has been transmitted correctly or not? Actually, it should be packet. So the transmitter sends a packet and then starts a counter, initialize a counter. So it starts counting time, and this counter goes on. Okay. So what happens after the transmission of the packet inside the receiver? The receiver does not send anything else until one of the two events occurs. The first event is the reception of the ARQ. Okay. If the first event is the arrival of the ARQ, then the transmitter goes on and transmits the next packet. Okay. This is the next packet, it's not the same as the next. Otherwise, and then repeats the same procedure. So once you start transmitting the packet, it means it initializes another counter. Okay. So here the counter starts counting from 0 to a certain number, then the ARQ is received, the counter is reset, starts from 0 again, starts counting time. What happens if after the transmission, the next event is the timeout? Okay. The counter starts counting, and there is a fixed time that is called the timeout. And if the counter arrives to the timeout before any ARQ is received, then the timeout expires. Okay. So if the timeout expires, then the sender will retransmit the packet. We transmit again the same packet. That is the basic mechanism. So once the sender has transmitted the packet, it has to wait. That is why it is called a stop and wait. So it does not go on immediately to transmit other packets. And it waits for an event. This event can be the arrival of the ARQ. In this case, the transmitter sends the other packet. The expiration of the timeout, in this case, there is the retransmission. Okay. When there is the arrival of the ARQ, what is the time that is taken by the ARQ to arrive back to the transmitter? If you have transmitter and receivers, the point-to-point case, that is the simplest case, you will have, this is the time diagram, you will have a propagation time, then the receiver has to transmit the ARQ, and then there is another propagation time value. Okay. So this time interval from when, in the case where there are no errors, so when the ARQ goes back, from the time that the packet has been transmitted completely to the time that the ARQ has been received is 2 tau, where tau is the propagation delay, plus T ARQ, where T ARQ is the transmission time of the acknowledgement. Okay. So the timeout has to be designed in order to be larger than this value. Otherwise, all the packets, all the timeouts will expire all the time. Okay, because if the this is the minimum possible delay of the ARQ. The ARQ cannot arrive earlier than this time. So if you design the timeout, that is the time from the end of the transmission until the timeout expires, smaller than this value, then stop and wait doesn't work, because all the timeout will always expire. So the timeout must be larger than this value. How much larger? Well, it's up to the design features. Okay, it's up to the designer. So you can select the timeout that is greater than this value or equal to this value. If the timeout is larger, then you are safer, because this value is predicted, okay, but there may be some extra delay in some cases. Okay? Or if you are not very if you're not able to predict the value exactly, then a margin is desirable. Okay, so you should design the timeout a little larger than that value. However, if you do the timeout too large, then you keep waiting for a long time in case of error. Because in case of error, the transmitter has to stop until the timeout is expired. So if the timeout is very large, then each time there is an error, the system stops for a long. And the error may occur both on the transmitted packet and also on the transmitted packet. And that is transmitted there. Okay. Usually, timeout is not actually defined in this way. So from the end of the transmission time to the expiration of the timeout, but in this other way. So it includes also the transmission time of the packet. Okay. You must be careful because this is a conventional definition. So in some cases it may include a T, some other cases may not. Okay. You have to look at or decide if you are writing the timeout yourself. Is that clear? Okay. So this is basically all we need to know about stop and wait, because it's a very simple protocol. There is, however, another issue, and the issue is related to the numbering of packets and of ARQs. Okay. Actually, packets must be numbered, and also ARQs must be numbered. And conventionally, the sequence of numbers of the packets is called SN. The sequence of numbers of the ARQs is called RN. Why numbering is necessary? Because if the packet is sent multiple times for some reasons, the receiver cannot recognize the duplication if there is no numbering system. And in particular, the receiver needs to know the number of the packets that are sent. And on the other hand, if the transmitter receives an ARQ, it should be able to correlate it to the confirmed packet, so the packet that is acknowledging. And so this is why we need also numbering of the ARQs, okay? Because the transmitter, when it receives an ARQ, if it is numbered, so if it has a number of the sequence Rn, then the transmitter can compare this number to the sequence number of the packets he has transmitted. So you can understand if the ARQ is what is the packet that is related to the specific ARQ. So at the first sight, numbering is not necessary in stop and wait, because since the mechanism is based on the stop and so transmit the packet and then stop, it looks like the packets that are, let's say, under uncertainty are the packet that is under uncertainty is only one. Okay. So one may ask why we should use the numbering system also in case of stop and wait. And the reason is represented by this case. So what happens if the ARQ is lost and the timeout expires? So in this case, the sender sends packets. Packets are correctly received, and also in this case, the packet is being correctly received. So the receiver sends back the ARQ, but the ARQ gets lost. So the ARQ gets lost. So when the timeout expires, the sender starts retransmitting the same packet, because for the sender, this packet has been lost. The sender has no ways to understand if the error was on the packet or on the ARQ. So the sender retransmits the same packet, but the receiver has already received that packet, and it has received it correctly. And in fact, the receiver has generated the ARQ. And the receiver has no way to know if this ARQ was lost or not. Okay? So once the sender retransmits the packet, then the receiver takes the new packet as a new packet if there is no numbering. Because for the receiver, the previous packet has been received correctly. And this is a problem because in this way you generate a duplication. This packet is on the receiver side will be sent to the upper layers, and then the next packet will be sent to the upper layers, but it's a replica of the same packet. So this is why you need to number the packets and also the ARQs. So what happens when you have numbered the ARQs and packets? Same case. Now the receiver, the sender sent packet number 2. The packet is up because it is received correctly, and ARQ number 2 gets lost. So the sender starts retransmitting the same packet, again number 2, after the expiration of the timeout. But now the receiver is able to understand that this packet number 2 has been transmitted twice. So it will drop the second copy of packet number 2 in order to avoid duplications, and it will send again ARQ of packet number 2. Because obviously, if the receiver has received correctly packet number 2 and generated the first ARQ, but the sender sends again packet number 2, it means that the second ARQ number 2 has been lost. So the correct procedure is to drop the second copy of packet number 2 and to generate ARQ number 2 again. When the receiver finally gets ARQ number 2, sorry, the sender finally gets that ARQ number 2, it can start transmitting packet number 3. So with numbering, this stop and wait is robust also in the case of the loss of the arcs. Okay. On these ARQ protocols, it's very easy to calculate efficiency. The efficiency is, by definition, the fraction of time in which the channel, where we use this retransmission mechanism, is used to transmit useful information compared to the total time. Okay? So it's the fraction of the time when it is used to transmit useful information. And the calculation of efficiency for stop and wait is quite simple in the case when we don't have errors, so we don't need to use any probabilistic approach. The A beta that is simple to use for efficiency is the ratio between T, that is the transmission time of a packet, and T plus TARQ plus tau. And that is the transmission time of the packet plus the minimum timeout you can design. And you can see from the picture that this is consistent. So basically it's the ratio between T and all these intervals. The efficiency of the stop and wait protocol is very bad, even in case when you don't have errors, because you take out T, so we simplify T from the top and bottom. Here we have this term that is 2 tau divided by T, and so when the propagation delay is large compared to the transmission delay, then here we have a number that gets very large, and so the efficiency goes down. So this protocol is very simple but not efficient in terms of the usage of the channel, and in particular it's not suitable when the distance is very large, and when the transmission time is very short. So frequency of the channel, the capacity of the channel is high. So how can we increase the efficiency of the ARQ protocols? We have to start using a new tool that is the transmission window. And the simplest ARQ protocol that implements transmission window is called the go back N. So it's a variant of the stop and wait. Instead of transmitting one packet and then stopping, now the transmitter is allowed to go on transmitting other packets, a limited number of other packets, even while waiting for the first act on the first packet. So instead of shutting down during the timeout, the transmitter can go on transmitting other packets. How many packets it can transmit? It depends on the size of the transmission window. The transmission window basically is a parameter that is limiting the number of packets that can be transmitted while waiting for the ARQ. So this is why the N usually is the size of the transmission window. But why go back N? Okay. Go back N because of the behavior when you have errors. When you don't have errors, what happens is what you see here. So assuming that the initial size of the window is the size of the window is of 8 packets, so it means that initially the transmitter that starts transmitting packet number 1 can transmit from packet 1 to packet 7 while waiting for the acknowledgement on packet number 1. Okay? So this is the transmission window. Transmission window initially is positioned with the beginning of the transmission window on number 1 and the end of the transmission window on number 7. Notice that here we are using the sequence numbers of the packets, so the SN numeration. So the transmitter starts sending the packets. What happens when the transmitter receives back the first ARQ? Okay, that occurs in this instant here. Okay? So the transmitter here is when the window window position of the window is from 1 to 7. The transmitter, while waiting for ARQ number 1 went on, so transmitted the packet number 2, 3, 4, 5, and 6. While he is transmitting packet number 6, the transmitter receives the ARQ on packet number 1. So what happens? The window is moved by one position. Okay. So now the new window goes from packet number 2 to packet number 8. The size is still the same, the size of the window, but the position of the window is shifted. And this is why this is called sliding window. Okay. Sliding window because each time a packet, an ARQ is received, the window slides on by one position. So when the window slides on by one position, moves here from the position from 2 to 8, it means that the transmitter can go on to transmit packet number 7, packet number 8, while waiting for the acknowledgement of packet number 2. Okay. Packet number 2 is still unacknowledged because the transmitter has received only packet number 1. And you can also notice that the position of the window is always placed so that the first number inside the window is the number of the first packet that has not been ARQed yet. Okay, so once packet 1 has been acknowledged, it gets out of the window because the window shifts by one position. So when the ARQ on packet number 2 is received, then the window slides on again, and so on and so forth. In this example, you can notice that since the size of the window is sufficiently large, this transmission will never stop. Okay? Because all the ARQs gets back before the transmitter has exhausted the window. So the transmitter is almost exhausting the window, but immediately an ARQ arrives, so the window slides on. Okay? So in this case, if there are no errors, the transmission never stops, and it means that in terms of efficiency, you reach the 100% of efficiency. Because since you are transmitting one packet after the other, there is always, the channel is always used to transmit useful information. Okay? So with the stop and wait, there was a limitation on the efficiency. With go back end, if you are able to correctly calculate the size of the window according to the times that you see here, there are always propagation time, transition time, back propagation time, and there are no errors, then you can go on indefinitely. So you reach 100% of efficiency. What happens if an error occurs? And this is why the protocol is called go back N. So when there is an error, it means that there is a timeout that expires before getting an acknowledgement in time. on time, the transmitter starts to retransmit the window from the first packet that has not been already hacked. Okay? So even if it has transmitted several packets, it starts transmitting again all the content of the window starting from the first packet that is not been hacked. And this is why the technique is called go back n. Because if the window is has a size n and it is positioned at the first packet that is not been hacked, it is all the content is retransmitted again in case of error. And how the transmitter knows that an error occurs, the mechanism is based on the timeout again. So it says the timeout has the same meaning as in stop and wait. So for example, we consider the same case or the same previous case. Window here has a size of 8 packets, so it goes from packet 1 to packet 7. 7 packets, sorry. Starts from packet 1, arrives to packet 7. The transmitter starts sending packet 1. Then it starts counting, initializing a counter. Counter conventionally here is initialized at the beginning of the transmission of packet 1. And goes on transmitting the other packets, because now the window is large enough, so it goes on waiting for packet number 1. In this case, packet number 1 arrives before the timeout expires. So the counter here stops at the arrival of packet number 1. The timeout is reset, it's cleared. The timeout, total timeout was there, but the ARQ gets in earlier. And since the ARQ on packet number 1 has been received, the window slides on by 1 position, so it goes from 2 to 8. Okay. In the meantime, the transmitter has transmitted also packet number 2 and packet number 3 and so on. Each time the transmitter sends a packet, it initializes the timeout. So the timeout of packet number 2 has been initialized here, and in the case of packet number 2 gets lost. So it's received with errors. It's discovered by the receiver, so the receiver does not send any ARQ. This implies that the timeout expires before the ARQ of packet number 2 is received by the transmitter, and until the packet number 2 is not received, the transmission window remains blocked there. It doesn't slide, because to slide on, it has to receive packet number, ARQ number. Okay. So at a certain point, since the transmission window is blocked, the transmitter will reach the end of the transmission window. So here the transmission window was moved by 1 position, so it was from 2 to 8. At a certain time, the transmitter arrives to transmit packet number 8, and then it stops. Okay. It stops until the timeout doesn't expire. And the timeout expires in this moment there. What happens when the timeout expires? We have the go back n phase. So the transmitter starts sending all the packets that have been already transmitted from 2, which is the first packet that has not been acknowledged yet, from 2 to 8. Okay. So all these packets are retransmitted, and it may happen that packet number 2 was lost, but packet number 3 and all the following packets were received correctly by the receiver. But in go back n, even if the receiver has received correctly the other packets, they are out of sequence because packet number 2 is missing. So in this simple technique, they are discarded, they are all thrown away. Okay. The receiver has a capacity of buffering one single packet. So if the packet that is that receives is in sequence, then it's okay. If it is out of sequence, it is discarded. So by this technique, by overcan, we have often to retransmit packets that actually have been transmitted correctly. But on the other hand, we have a technique that is quite simple. In order to improve this, so to avoid retransmitting packets that have been actually transmitted correctly, there is the other protocol that is called selective repeat. With selective repeat, the receiver can ask to the transmitter to retransmit a specific packet. But on the other hand, the receiver needs a buffer to temporarily store all the packets that are out of sequence, momentarily out of sequence. So it is more complicated in terms of buffering structure. Okay. In overcan, the receiver ignores all the packets that have been received out of sequence, and this is much simpler. Now, since the receiver has this property that always discard packets that are out of sequence, it means that it also implies that the packets that are the ARQs that are sent by the receiver will always be for packets that are in sequence. Okay. So in this case, we can use the cumulative ARQ, or the ARQ message can have a cumulative meaning. For example, here we have packets 1, 2, 3, 4, 1, 2, 3, 4 that are transmitted waiting for the ARQ on packet number 1, okay, because the window it goes from 1 to 7. Maybe that the receiver receives everything well, but maybe that when the receiver should send the ARQ of packet number 1 back to the transmitter, for some reasons the return channel is busy. So the receiver cannot immediately transmit ARQ number 1. Okay. And also the same for on the packet number 2. But all the packets have been received correctly. So when the channel, the return channel gets free again, the receiver sends ARQ number 3. ARQ number 3 is considered by the transmitter as the acknowledgement not only on packet number 3 but also on packet number 2 and packet number 1. And that is correct because if the receiver sends an ARQ on a given packet, since the receiver always discards packets that are out of sequence, it means that it has also received correctly all the previous packets. So ARQ number 3 is a cumulative, and in fact we see that the window was 1 to 7, and when ARQ number 3 is received by the transmitter, the window moves by 3 positions. Okay. It's closed on, it slides on, not by 1 position, but by 3 positions, because the last acknowledgement packet is 3, but this implicitly implies that also packet number 2 and packet number 1 has been acknowledged. So the receiver, the transmitter moves on the window from 4 to 10. Okay? So this is a way to be robust in case ARQs cannot immediately be transmitted to the receiver, or in case they went lost. So maybe ARQ number one or ARQ number two, when it lost during transmissions, but ARQ number three is received correctly.
It's another kind of co-mechanic. You
What?
take the ARQ and you don't have the timeout that the reset time
No, this is, of course, ARQ number three here in this case must arrive before the timeout expires.
But it's the same as before, or it's changed?
It's the same as before. Actually, yes, actually here should stop at 7, not at 8. It's a mistake. So actually, the transmitter, since the window is from 1 to 7, and here the timeout, no, because the timeout here is longer, no, it's longer than before.
And then you expect 1 app for any packet. Not 1 app for each packet, but 1 for a group of packets.
The transmitter doesn't know actually. There is a mistake in this case because this packet number 8 cannot be attached to number 7. Here the window stops because timeout did not expire, and so it doesn't start go backend operation, it doesn't start retransmission. In fact, the timeout here is long enough. But the window is from 1 to 7, and so it should stop here. This rate, I have to move it.
How the sender can know that actually is okay for 3 packets and not just for 1? Because it's like a different version of?
No, it's the same because in backend we know that the receiver cannot store packets that are out of sequence. So if the transmitter.
Okay, so if the receiver sends an ARQ, it's because it has received all the packets in a sequence. Okay.
If the receiver sends this ARQ3, it means that he also got number one. Let's see if I can do this modification on the fly. It's a little bit slow. Okay, now it's this should be the correct version. So packet number 8 can be transmitted, but the lag because is blocked.
Excuse me.
Yes.
So for this reason, I have a limit on the ARQ that I can accumulate in a single ARQ.
No, in principle, there is no limit. Actually, no, there is no limit. There is a limit. These numbering systems are always cyclic. Okay, so you have to the numbering of packets goes from 1 to a certain number, say capital N, and then goes back to 1. So, for instance, in this case, the number should be the maximum number should be 7 actually.
But if it takes into account 7 buckets, it will be a starter store because I have to wait, yeah, before sliding in.
Exactly.
If it goes until 7, so the size of the maximum size of the window, the maximum, the minimum module of numbering should be greater than maximum window size plus 1 in global game. Actually, this dimensioning actually have been taken out of this course. So, but if you want, the rule is that the maximum size of the transmitter buffer, that is equal to the maximum window size, plus the size of the receiver buffer should be less than the numbering module. In case of global cannons, the receiver buffer is always one position. Okay. So this is why we use that rule. With selective repeat, different. But in any case, here in these examples, we don't use the cyclic numbering. So you can see that we go from 1 to 7, then 8, and so on. That is a little bit simpler than in the reality. All numberings are cyclic and should be dimensioned in a correct way.
Should the timeouts not be shorter?
The timeout should not be shorter. It can be, it must be larger than the transmission time plus twice propagation delay plus the transmission time of the ARQ. And this is the same that we have in selective. But I can do it larger. I cannot do it shorter because otherwise, also in this case, it will always expire.
I mean, I cannot use the window, right? Until the timeout is over.
No, the timeout is for the retransmission. Okay? The position of the window is given by the ARQs. So, when you don't receive the ARQ, the window is fixed. And this is the dependency of the timeout. If you make the timeout too short, then the system doesn't work. In this case, it is longer than the minimum, so it's accepted, it's correct. So what is the optimal window size that we can make? And so just following what we were just saying, the minimum timeout is given by the sum of transmission time twice the propagation time plus the transmission time of the ARQ. So if we want that the receiver, the transmitter, in case of no errors, never stops transmitting, so if we want to achieve 100% efficiency in case of no errors, with absence of errors, then we have to design the window size so that during this interval that goes from here to here, the one that is presented in the picture, the transmitter always continues to transmit. So the size of the window should be designed if we want to have to achieve this continuous transmission according to this expression. So you take the smaller integer greater than the ratio between t plus tn plus twice tau, which is this interval here divided by transmission time of the packet. Okay. So if you divide this interval by this time, you have the number of packets that can be transmitted in that interval. So if the size of the window, of the transmission window, is larger than this number, then in absence of errors, go backend achieves 100% efficiency. If you do the window smaller, then also in case of when you don't have errors, the transmitter will stop. Because the first up can come not earlier than t plus t up plus twice tau. Okay. This is also this sum is also called the round trip time of this system. So it is we need to know the round trip time of the system in order to design the windows in a appropriate way. There are cases, however, when this round trip time is not known. Okay, this round trip time is typically known when you have a point-to-point connection. So if the system is, for example, a layer 2 structural layer 2 protocol, then the sender and the receiver are connected by a physical link, so you know for sure the propagation delay, because especially the physical link is a wired link, and you know also the transmission time of the transmitter, the transmission time of the receiver. And if you have fixed size packets and fixed size ARQs, then that number, the round trip time, is deterministic. In the other cases, the number is, in many other cases, the number is not deterministic. For example, if we are implementing go backend at the transport layer, we are considering an end-to-end system, two hosts in communication. Okay, but then you know that when two hosts are in the communication, they are communicating with a logical link. However, this logical link is not a physical link. It's not a point-to-point link. Okay, so as we have already seen while talking about the application layer, here, for example, the capacity of this link can only be given in an approximate way as an average capacity. And moreover, packets are then transmitted on the network layer, that is the IP layer, crossing several hops. And in these hops, you have the routers. And in the routers, packets, when they arrive at the routers, are stored into queues. Okay? And so, as we have seen in the first part of the course, when you have a queuing system, that is here, you have a waiting time in the queue. So your packet that arrives here experiences a waiting time here in the queue, which depends on the state of the queue. How many packets are already in the queue? And this cannot be determined a priori. You can only have a statistical evaluation of the round trip time. Okay, so when we are implementing this ARQ mechanism at transport layer, the round trip time is a random variable. But here we need round trip time, for example, to design the windows. So how to do to solve this problem? The first solution is the CV1. Since we have this uncertainty, we apply a very large margin. So start with the minimum possible delay, round trip time, and that is, for example, the physical round trip time when all these waiting queues, waiting times are 0, and we multiply it by a large number. This makes, however, the protocol very inefficient, okay? Because then the timeouts are very large and so on. The solution that you will see in TCP is to periodically estimate the round trip time by making measurements. Okay, so in in TCP protocol, which adopts ARQ as retransmission techniques, the round trip time is periodically measured from the source and destination, and so the windows and the timeouts are adjusted accordingly. Okay. We will see this later on, however. The use of NAC is possible, and it is an advantage because in many cases it can shorten the time of the retransmission in case of error. Okay. So in case of error, we don't have to wait until the end of the timeout. So the transmitter does not have to wait until the end of the timeout if the transmitter knows in advance that the packet has been lost. How can it know in advance? If it receives an negative acknowledgement for a certain packet. Then the transmitter can immediately stop the transmission and start retransmission before waiting for the timeout. There is, however, a problem. When the packet is lost, because it has an error, the receiver cannot know for sure what is the sequence number of the packet that has the error. The packet is completely locked, okay? Because maybe the error is exactly on the field that is number in the packet. So the only way the receiver has to understand that the packet has been lost is to receive correctly an out of sequence packet. So if another packet that has a larger sequence number. So by the correct reception of the packet, I know that all the packets that were missing in the sequence are lost. So we can the receiver can send the NACs for those packets. So this mechanism works only when you have guaranteed order delivery, like for example in the go backend case. What happens from this example? Here you have a window that goes from 1 to 9. The transmitter starts sending packets 1, 2, 3, 4, etc. Packet number 2 got lost. So packet number 1 is active because it is received correctly. When the receiver receives packet number 3 correctly, because packet number 3 arrives correctly, the receiver knows that packet number 2 has been lost. So it can send an ARQ on packet number 2, and even if the timeout here should be increased or is very large, immediately when the transmitter receives the NAC on packet number 2, it starts the retransmission operation. So it starts retransmitting from packet number 2, packet number 3, and so on, without waiting to get to the end of the window. And another important aspect to consider in these systems is the full duplex case. The full duplex case is simply the case when the transmitter is A, the receiver is B, and so information flow goes from A to B. Then on the return